let us start with some examples. Example number 1. We are asked to specify the region of convergence for the following. Regions of convergence for the following. We are going to give you the sequence. You have to compute the Z transform and then tell what is the region of convergence. So example number 1. X of n is equal to delta of n plus 2 plus 3 delta of n plus delta of n minus 2. Okay, so x of n is a sequence which has got zeros and then a value of 1, 0, 3, 0, 1 and then zeros after that. Okay, so this is the origin. And x of z can be written as z power plus 2 plus 3, which is the constant term, and z power minus 2. Okay, so the region of convergence will be, it's a polynomial, so therefore it will be the entire z plane. Are the extremities excluded? Z equal to 0, is it included or excluded? It has to be excluded because you have z power minus 2. Okay, if you include z equal to 0, the z power minus 2 will go to infinity. So excluding z equal to 0. How about z equal to infinity? Same problem, because now we have z squared. So z equal to infinity cannot be included. So you have to exclude both the regions or both the values. So how will you write the region of convergence? Mod z strictly greater than 0, strictly less than infinity. That's an expression for the entire z plane, but 0 is excluded, infinity is excluded. So that would be a way for you to remember and apply the z transform. Okay, example number 2. X of n is equal to 2 power n u of n plus half power n u of n. Remember, two terms, you will get region of convergence for both, and you must look at the intersection of the regions of convergence. So x of z, first term, 1 over 1 minus 2 z inverse. Okay, and the second term is 1 over 1 minus 1 half z inverse. Okay, what are the respective regions of convergence? Mod z greater than 2, because 2 z inverse must be less than 1, therefore mod z will be greater than 2, and in this case it will be mod z greater than half. Okay, so draw the region of convergence, very important. Okay, this is the circle with radius half. This is the circle with radius 1, radius equal to 2. Okay, so let's write it down. This is mod z equal to 2, this is mod z equal to half. And remember, both are right-sided sequences. And if you have, when you have multiple right-sided sequences, you are looking for the region where both sequences exist. So you must look for the outermost pole. So the first pole occurs at z equal to 2, the other one at z equal to half, the outermost pole is z equal to 2. So the region of convergence will be mod z greater than 2. So basically the region outside of the outer circle. Right-sided sequence, the outer pole is at z equal to 2, and therefore we get this as our region of convergence. Okay, so let's just write it down. So ROC1 was mod z greater than 2. ROC2 was mod z greater than 1/2. Okay, so ROC1 intersection ROC2 was the region is mod z greater than 2. That's the point where both of them exist, and therefore okay. some quick questions. Is this a right-sided sequence? What you have obtained? Right-sided? Yes. Right? Both are right-sided sequences. Are they causal? Causal? Yes. By looking at the region of convergence, can you say that they are causal? Not quite. You can say that they are right-sided sequences, but you have to check the inverse transform to check whether they are causal or not. But right-sided sequences definitely, and in this case, they also turn out to be causal. Now, very important question: is the sequence absolutely summable? Okay. That's another way of asking, does the DTFT exist? Because the condition for the existence of the DTFT is that the sequence must be absolutely summable. So, does the DTFT exist? Question mark. Look at the region of convergence. Where is z equal to 1? Z equal to 1 is sitting inside between these two. Okay, so between half and 2. So, you can think of it as the red dotted circle as the unit circle. Okay, it is lying between the two poles, but it is not in the region of convergence. Okay, so mod z equal to 1 not in the region of convergence, which means that the sequence is not absolutely summable. Not absolutely summable. Okay, summable, and therefore DTFT does not exist. DTFT does not exist. I hope you are comfortable with the steps that we have done and the explanation and how we have gone about doing the calculation. All right, let's look at a third example. Example number 3. X of n is equal to alpha raised to the power modulus of n. And we are given that alpha is a real number in the range 0 through 1. Okay, now is this a decaying exponential or a growing exponential? Alpha is less than 1, so therefore for positive powers of n you will get a decaying exponential. Okay, so we can make the following statement: it is a decaying exponential for n greater than 0. What about n less than 0? If you have not taken the modulus there, it would have become a growing exponential. But because we have taken the modulus, it is also a decaying exponential for n less than 0. So, given that they are both decaying exponentials, there is a good chance that the Z transform will exist. So, let us do the computation of the Z transform. So, x of z, first step, write down the general expression n equal to minus infinity to infinity alpha raised to the power mod n z power minus n. Since the modulus acts differently for positive values of n and negative values of n, we will split the summation into two parts. So, split it as summation n equal to 0 through infinity. These are positive values of n. So, alpha raised to the mod n can be written as alpha power n z power minus n, and the second term will be summation n equal to minus infinity to minus 1, because 0 to infinity has been captured in the first summation. And now these are negative values of n. Modulus of n will produce a positive value. So, we write it as alpha raised to the power minus n. So, minus of a negative value will give you positive value. So, the modulus for n greater than 0 becomes just alpha power n. The same modulus for negative powers, you have to write it as alpha power minus n, and of course z power minus n. Now, just simplify. The first term will be 1 over 1 minus alpha z inverse ROC mod z greater than alpha. Second term, just do one extra step of substitution. This can be written as summation m equal to 1 through infinity alpha z. Right? I've changed from m equal to minus n. So this is a geometric series which is given by alpha z divided by 1 minus alpha z. The condition terms for condition of this will be alpha z less than 1, which is the same as mod z less than 1 over alpha. Okay, so the region of convergence for the second term, this expression, we can write it as plus alpha z divided by 1 minus alpha z. The region of convergence is mod z less than 1 over alpha. The second term represents a left-sided sequence, the first term represents a right-sided sequence. Now we must look for the intersection of both these. So ROC1 intersection ROC2. So let's take a specific example. If I take alpha equal to 0.5 as an example, then this will be mod z greater than 0.5. The second term will be mod z less than 1 over 0.5, which is the same as 2. The intersection of these two will give me a ROC which is greater than 0.5 less than 2. Okay, a two-sided sequence where the limits are bounded between the two poles. One of them is a pole at alpha, the second one is a pole at 1 over alpha, and then we get the expression that so I'm trusting that you are starting to feel comfortable with the computation of the Z transform. Write down the general expression, get the limits correctly, and then do the expression for the Z transform, and then correspondingly we get a condition for the region of convergence. Okay. As you look at these examples, I would also encourage you to look at some of the examples that are there in the textbook. Also try out some practice assignments that will give you, you'll gain some confidence as you do that. But here in the class also we will try to do a number of examples so that then you will feel comfortable with the concept. All right. Let's look at a couple of more examples before we move into the Z transform pairs. So I believe we are on example 4, right? Example 4, correct. Example 4. Okay. We are given the expression x of n is equal to 1/2 1 plus minus 1 raised to the power n u of n. A very interesting type of sequence. Now, if you were to plot it, you will find that this is a sequence which has got all zeros up to the point where n equal to 0, and then it takes on a value equal to 1. Then the next term for n equal to 1, it is 0, for n equal to 2, it is 1, n equal to 3, it is 0, n equal to 4, it's 1, and this pattern repeats. So this is 0, 1, 2, 3, 4. All the even terms have got a value equal to 1. They look like the unit step. The odd terms have been forced to a value of 0. Okay, always good to write down the sequence. So it is all zeros up to the point where you get the origin. Okay, all zeros up to this point, and then from this point on you alternate 0, 1, 0, 1, 0, 1, dot, dot, dot. That's the expression that we have. Okay, so this is x of n. X of z, directly from here, write down the expression corresponding to the first term. It is 1, then you have 0, then you have z power minus 2, then you have z power minus 4, and so on. Okay, this is also a geometric series, 1 over 1 minus z power minus 2. What is the condition? Z power minus 2 must be less than 1, which means mod z squared must be greater than 1, which is the same as mod z greater than 1. Okay, only when mod z is greater than 1, mod z squared will be greater than 1. So this is the region of convergence. This is the region of convergence. All right. Now, there's a very interesting way of looking at this particular problem in a second alternative way. Let's look at that. I'm going to look at it as two sequences, half u of n plus minus 1 raised to the power n 1/2 u of n. Two sequences. Supposing somebody didn't tell me that I'm going to add them up, I think of them as two separate sequences for which I want to compute the Z transform. Okay, so x of z in this case will be 1/2, and we know the Z transform of u of n, 1 minus Z inverse, region of convergence mod Z greater than 1. Correct? Second term, a plus 1/2. Now, I just want to make sure we don't make a mistake here. So, summation n equal to 0 through infinity minus 1 power n z power minus n. Okay, I can write this as, I'm just going to write a couple of extra steps, 1/2 n equal to 0 through infinity minus z power minus n, because minus 1 power raised to the power n raised to the power of minus n both are the same. So, I write a minus z raised to the power minus n. This is a geometric series with a common ratio minus minus z inverse. Okay, so this can be written as 1 over 1 plus z inverse, where the common ratio minus z inverse must be less than 1, or if I put the condition, this will be mod z greater than 1. It turns out that for both of these terms, the common region of convergence is the same. Okay, this comes out to be 1/2 1 over 1 plus z inverse with mod z greater than 1. Okay. Now, from this second way of looking at it, we can say that the x of z is 1/2 of 1 over 1 minus z inverse, 1 over 1 plus z inverse with a region of convergence mod z greater than 1. Are the two expressions the same? So, we have an expression number 1 and expression number 2, and please verify that expression 1, expression in equation 1 is the same as the expression in equation 2. Straight, very simple simplification. I'm sure you will be able to do that without much of a difficulty. Okay. Now, one last example, example number 5. Again, you may be able to write it down almost by inspection, but I would like you to just write down the steps so that you are able to. So, this will be minus u of minus n minus 1. Okay, first thing is always a good idea to sketch it. Okay, this is u of n shifted to the right by 1 and then time reversed. So, make sure you get the sequence correctly. And then there is a negative sign. So, we have the following, you have all zeros to the right, and from here on you have a value of minus 1. So, this is a value of minus 1. Okay, so, it goes on both sides. Okay. So, x of z is equal to, keep the minus sign outside, it goes from n equal to minus infinity to minus 1, okay, z power minus n, all the value, the minus sign outside captures the fact that all of them are negative values. So, this is given as, I can change the variable. So, this becomes minus summation m equal to 1 through infinity z raised to the power m. So, this can be written as minus z divided by 1 by z. Can also simplify it as 1 over 1 minus z inverse. Okay. Now, notice that this is the z transform of a sequence that you know. This is the z transform of u of n. Okay, Z transform of U of n. There the condition was mod Z greater than 1. Okay, so in this case the condition is mod Z less than 1. That's the condition for the geometric series to converge. So basically you get a right-sided sequence for mod Z greater than 1, left-sided sequence for mod Z less than 1, and so again always good to sketch the sequence, write down the expression for x of z, apply the limits and get the correct expression that we have. Alright, let me ask you a question that will require you to apply some of the principles that we have studied so far. Suppose we are given x of n as a finite length sequence, and it is absolutely summable. Okay, what does that mean? Summation n starts at some integer n1 and goes up to another integer n2. Okay, so basically a finite length means that these two are finite values. They can be positive or negative. Modulus x of n is less than infinity. Okay. Now, first question, does this imply that, I put a question mark, okay, does this imply that x of n is a bounded sequence? Remember what we had discussed in the very first unit. When do you call a sequence as a bounded sequence? For every value of n, it must satisfy a finite upper limit. Okay. Now, unless a sequence is bounded, it cannot be absolutely summable. Supposing one of the values went to infinity, then the sequence, when you do the absolute summability test, that will also go to infinity. So if somebody says that a sequence is absolutely summable, that implies that every sample that you have added has to be bounded. So the answer to this is yes, it has to be bounded. So modulus of x of n must be less than some finite upper limit. We call that as b of x. Okay, so given that a sequence is finite length sequence is absolutely summable, first thing that you will be able to state with confidence is that it is a bounded sequence. Okay, now based on this, tell me if the following statements, whether they are true or false. True or false. Okay, the first one, the ROC is the entire z plane, ROC of x of z is the entire z plane. True or false? Okay, you can say, you have to add something before you can make a statement whether it's true or false. You have to say it will probably exclude, right? It is a finite length sequence, so the entire z plane is the correct answer. However, z equal to 0 and z equal to infinity have to be assessed. If there are negative powers of z, 0 will be excluded. If there are positive powers of z, so except possibly z equal to 0 and or z equal to infinity. These two could be have to be excluded. So under that additional condition, you cannot say blanket say it's an entire z plane is ROC. Those exclusions will be there. Under that conditions, this will be a true statement. Okay. Second, the x of z always exists. What does that mean? That there is some region of convergence that you can specify. In this case, of course, the whole z plane is there, right? So therefore, x of z exists is a true statement. Okay. The third statement, the DTFT of x of n has uniform convergence, not the mean square convergence or the the delta functions and all of that. There is uniform convergence. Okay, the question that you would ask is, for the DTFT to exist, the ROC must include the unit circle. What is the ROC? Entire Z plane except the two extremities. So is unit circle included in the ROC? Answer is yes. Under that condition, you can confidently go in and say this is also a true statement.